Let me do the recording first. Okay, yep, I'm recording now. Okay, so these are the questions that we're going to discuss for this tutorial, 1, 2, 4, 5, 6, and 11. Let's look at question 1 first. Okay, so I hope it's clear enough. So this is question 1 for tutorial 3. Okay, ABC. So let's look at part A first. Supposing A, B are independent, then show that A, C, and B are independent. Okay, actually, we have this very interesting feature over here. Okay, I'm not sure whether you guys are aware of this or not, so I just put as remarks here. Okay, actually, all these are equivalent. Yeah, so that is if you have two events, A, B are independent. Okay, so this is actually equivalent to say that the complement of A and complement of B are independent. And also, it is equivalent to say that A and B complement are independent. And also, it is equivalent to say that A complement, B complement are independent. Okay, so please take notes of this. Okay, here I only show you the proof of the first equality, the first one actually not equality, just to demonstrate A, B independence implies A complement and B independent. In fact, if you are taking A, B independent, so the remaining you can take any combination of A, B, A complement, B complement. So any two of them must be independent, right? So please take notes of this. Okay, anyway, let's look at question 1A. A-B independent, show that A-B independent, and then show that A complement and B are independent. I'm reading your message. So I can't remember who posed the question. They said they couldn't understand the proof. Okay. Actually, the idea is not difficult. Okay. So let's look at question first. Question 1A. 1A. All right. As usual, let's look at supposing this is the diagram. So you have this diagram here. Okay. And supposing A. This is your A. This is your A. So this is A, and this is A complement, right? Okay, so you just look at so A will be the blue color things, and the complement of A will be given by okay, maybe I don't not to mess up this. Okay, so let's say this is the B. This is our B. Okay, maybe not to look at our B first. So I think okay, so A is the blue color, right? So and complement of A will be the green color. Okay, so then you look at, let's say this is our B. Okay, so you can see this B consists of two portions. So one portion will be here, and the other portion will be this, right? Okay, there will be two portions over here. Then from this diagram, you can actually see B can be written as, so just look at the blue color portions. So that will be just your B and A, right? So the blue color portions, and together with the green color portion, so which is your B and AC. Yeah. So this is what we can see from here, and you can see these two parts are destroyed. Yeah. So these two parts are destroyed. Okay, B can be written like this, and also B and A together with B and AC are destroyed. So I think this is quite straightforward. Okay, now using this, then we can apply the formula. So we can have P of B can be written as P of B and A plus P of B and this. And because of AB independent, so this one will be equals to, I think after this will be straightforward. We have PB, PA plus PB and AC. So this is just simply because of AB are independent. Okay, we have this. So, and we rephrase this, so it end up to be P of B and AC will be PB minus PB, PA. So I think the remaining are straightforward calculation. So we can have this will become PB multiplied PAC. So this equals to this by the definitions, that we can make a conclusion that B and AC are independent. Okay. So basically that will be this one. So in general, it will be like this. Yeah. So in general, again, another remark. So in general, if you have a A1, A2, A3 up to, let's say, up to AM, form a partition for omega. So let's say you have a M subset, so they are destroyed, and the union is equals to the sample space omega, which means they form a partition for it. Then I'm going to have B must be equals to B and A1 union B and A2, so up to B and A M. So this is a general case. Okay? So in this case here, we have A1 is equals to A, and A2 is just equals to the complement of A. Right, so I think once you aware of these decompositions, furthermore, it can be written like this, and furthermore, all these are destroyed. I think maybe I can put here. And we have furthermore, we have this all these B and A1, B and A2 up to B and AM, all these are destroyed. So I think it's quite straightforward. Again, for our questions here, we only consider two portions, A1 and A2O here. So let's carry on to, I think question 1B and C are quite straightforward. Huh? Okay, so let's look at the settings over here. So B, there are two statements over here. So AB, independence, okay, and after that, PA greater than 0, PB greater than 0. So, and then we ask whether AB are mutually exclusive or not. Right. So I think this is quite straightforward. So there is, we have two hypotheses. So there is, first of all, AB are independent, okay, together with PA greater than 0, PB greater than 0. Do that implies that these two are mutually exclusive or not, so which means they are disjoint or not. So yes or no, okay. So I think the C will be similar. C will be just when, if we know AB are mutually exclusive, so that means they are disjoint, and PA, PB greater than 0, then we want to check whether they are independent or not. Okay. So this is question 2B. So I think the answer is quite straightforward. So the answer will be, I think, okay, maybe what we can do is we can check for that. So when AB independent, we're going to have this. When AB are independent, so we're going to have this. PA and B must be equals to PA multiplying PB. Okay, when PA and PB are non-zero, so this must be greater than 0. Okay, and this is just simply because we have our hypothesis PA positive and PB are positive. When PA and PB are positive, then this must be positive. So then we can know that hence this cannot be empty set. And so AB cannot be not mutually exclusive. Okay, so using similar arguments, so we can solve part C. Okay, part C will be again similar. So we are assuming AB mutually exclusive and PA and PB greater than 0. Can we check whether they are independent or not? So of course, this is no, right? So we can see when AB equals 0, these are empty. So that means I'm going to have PA and B must be 0. And also when PA greater than 0, PB greater than 0, so I'm going to have PA multiplying PB must be greater than 0. So that means these two cannot be the same, right? This left-hand side cannot be equals to the right-hand side. So then we can see hence there cannot be independence.
Oh, I think because the answer, the hint says that they are independent.
The hint said they are independent.
Yeah.
Oh, okay. So typo, so should be not independent.
Oh, okay.
Okay. So thank you. Please make a corrections for the answer. So it should be not independent. Oh yeah. Okay, so please make a correction. So there cannot be independent. Oh, I think using this line will be clear. All right. Okay. So let's continue to question 2. Actually, what's the problem with question 2? Let me see. Oh, I have another proposal. Question 7 and question 8.
Just 8.
Oh, okay. So 7. Okay. So number 8. Okay, never mind. Any issue with question 2? Okay, no. Okay. All right. So I might just look at question 2 first. Whether they are in. What's the problem with this? Okay, so you look at here. We look at families with 2 children, and suppose that all the possible distributions of gender are equal likelihoods. Okay, so let's look at here. First of all, we look at a family with 2 children, right? So that means in this case, our sample space consists of 4 outcomes. That is, the first is a girl, the second is a girl, and the first is a girl, the second is a boy, and the first kid is a boy, and the second kid is a female, and finally, both children are male. Yeah, so that means we're going to have 4 of them, right? So, and we assume that there are equal likelihood. So that means P of, they are having the same probabilities, right? So that means all this must have the same probability. So they are all equals to 1/4. Okay. Okay. Next, A be the event that a family chosen at random has at most. So at most 1 boy. At most, that means cannot have 2 boys, right? So that means in this question, we can say A must be either both children are girls, the eldest one is a girl, or the small one is a girl. So this is A. And B, the event that the family has chosen, or this is of, as children of both gender. So that means in this case, B will be equals to FM or MF, right? So I think now it's very straightforward. So then from here we can see PA must be 3. The probability of the event A must be 3/4, and the probability of the event B must be 2/4. And I think it's clear that B is included in A. So PA and B is actually same as this. That must be 2/4. So I think it's clear, right? So this one can never be equals to PA multiplying PB. So then we can make a conclusion. Hence, so AB is not independent. So I believe it's straightforward, right? These questions. Okay, so I think the next one will be more challenging. Question 4. I think question 4 is also quite straightforward. Right, so let's proceed to question 4. All right, this. So this is actually a general situations. So without having any assumption on AK, whether independence or not independence. Okay, we just have a sequence of events AK, and we have another event B. We just want to show that B and lim sup AK will be just lim sup B and AK. Okay, to do these questions, so we just need to recall several identity, right? Okay, the first identity will be the general identity for set. So this is actually we so-called the, I think should be distributive law, okay, for set. Okay, so there is Z intersect union of n. Okay, n can be running from n index 1 to infinity or 1 to 5, something like that, Cn. So this is just equals to, I think maybe union of, okay, running index, Z intersect Cn. Maybe I put it over here. So likewise, we can have another identity, so which is similar to this intersection. So it turns to union intersection. So again, n could be a running index running from 1 to infinity, or maybe 1 to 5 or 1 to 10, doesn't matter. Okay. Again, n is a running index, so Z union Cn. So I believe this is quite straightforward. So what you can do is you may assume this is a product, this is a plus. Okay, so then we can have a similar idea. So let's say if you look at a number, you may assume this is a product, this is a plus. Okay, you may assume this way. So for example, if you have x multiplying a plus b plus c is what? Which is just equals to x multiplying a plus x multiplying b plus x multiplying c. Okay, maybe instead of we try to follow the same pattern. X multiplying, let's say you have a C1 plus C2 plus C3 and so on. So which is just equals to Z multiplying C1 plus C2 and so on. So then it ends up to be you summating this multiplying Cn. Okay, so you may have this kind of analogies over here. So this is the first properties that you can have. Okay, next one, we just need to recall the definition for lim sup of event. So the second, the definition for limit. Okay, so where is it? Let me check. So, so this one you refer back to. This is remark 0.4.1. So this is in chapter 0. So limit supremum of AK. So according to the definition, so which is just equals to the intersections of n from 1 to infinity of Bn. And what is your Bn? So Bn will be equals to this, the union of union of AK, K running from n to infinity. Yeah, you may assume, not may, actually, this is how we define B. B is the union of all the AK begin with n. So you may assume lim sup will be just, this is equals to infimum supremum of AK. Okay, so K running from n to infinity, and this one n running from 1 to infinity. Right, so that's why this will be this can be written as infimum of n greater. Okay, maybe if you want, you can use some non-standard symbol. So you can say this is intersection will be infimum n from 1 to infinity. So the union, in a way, you can say union means supremum k running from n to infinity. Okay, of course, this is not standard notations. You just to express it so that you can get a pattern for the symbols over here, right? Okay, once you're aware of this, I think we can solve our questions here. So come back. So we want to show this equality here. So let's look at these solutions. B intersect limit supremum of AK, right? So this is equals to B intersect. Okay, so according to, just refer to these definitions. So intersection of this Bn. This is your Bn. Okay, you have an intersections. So actually, if you're, I think after expanding this will be a better. So if you can, this can be written as Bn, B1, B2, and B3, and so on. Okay. And so this one can be written as intersections of this Bn, Bn, which means you can see this can be written as B. Okay, maybe I'll put it over here. Bn, B1, Bn, B2, and Bn, B3, and so on. Right? You can see these two are the same. Okay, next, what is your Bn? You refer to our construction or definition of Bn. So this one can be written as this. Okay, so here's we applying the distributive law. So then it turns out to be, so here, so then it just equals to this. Equals to this. Okay, so you go back to this. Okay, so you have intersections, unions will be lim sup of AK, right? And if you look at it, so that means this one will be just equals to limit supremum of K approaches to infinity of B and AK. Okay, so that's it. So this is what we want to verify over here. Okay. Right, so this is actually not so difficult. What you need to do is, first of all, just to recall this formula, okay, these two formula. What you can do is you may assume intersection as products, union as summations. So there is, you have a similar pattern. Okay, so that's the way. So next will be just need to recall the definition for limit supplement AK. That is in remark 0.4.1. Okay, having these two identity in mind, then you should be able to solve this question easily. Okay, so yeah.
Sorry, doctor, I just want to clarify something. You know, when you write lim sup, like the last line there, lim sup k to infinity.
Here. Okay, lim sup k to infinity.
The last line. Yeah, when you write, because I noticed that the textbook, you know, they write it in a different way.
How do they write?
Yeah, they just write.
How do they write?
Like lim sup, and then they just put a n. They don't put a to infinity or anything. You know, like
okay, yeah, I know. Actually, you see, this is all symbol. Okay, symbol. Sometimes they use shorthand. Okay, so for as long as you can understand the symbol, that's it. Okay, so in fact, all these are same meaning. Okay, so sometimes, for example, we can just write lim sup AK. Okay, some that prefer M or N. Okay, maybe M. Lim sup AM and just one M here. And lim sup AM, M to infinity. So all these three are the same meaning. Okay, just a symbol. So it's just whether you want to express it in how should I say, in a complete form. Okay, this is the most complete form, so we should express it in this way. Okay, lim sup M to infinity for AM, or if you don't want M, you can replace with some other indexes like N, K, whatever symbol that you like. Okay, however, you know, sometimes we are person, right? We are all lazy, so we want to write so many things, so we just simply write lim sup M AM, or we can make it even more easy, lim sup AM. But you just need to understand these three things represent the same meanings. Okay.
Okay, thanks.
Just some shorthand. You know, we are person, right? We are all lazy, right? So, for example, some we just write EG, and some we just write EX. Stand for examples. Okay. Just some shorthand for it. But you have to understand the meaning for it, right? Get it?
Yeah, thank you.
Yeah. All right. So likewise, you can see the textbook. Some they just simply write lim XM. Okay, or lim XMM, or lim XM and approaches to infinity. Yeah. So of course, this is the proper way. But like we just use some shorthand. We just write like this. Okay, provided the indices is understood N here. All right. Okay, so next, what questions? Questions 5. Okay, question 5. Okay, question 5. Before we do question 5, we just need to recall one theorem, one theorem. So this is in chapter 3, lemma 3.1. So we have this Borel, so-called a Borel-Cantelli lemma. We have 2 versions, version 1 and version 2. Okay, we have A and B. So let's look at B first. The second, or maybe instead of A, B, I'm using first and second. Okay, so this is actually we know known as the first Borel-Cantelli lemma. This is so-called the second Borel-Cantelli lemma. Okay, for the second one, supposing we have a sequence of events AK, so they are all independent. Okay, AK are independent, and what is this? The first one, when infinity. Okay. So this is infinity. Okay, so then AK independence and the summating of PAK is infinity, then P of limit supremum of AK is equals to 1. So for the first version, it's much more easier. We do not require the events to be independent. We just need to know, provided the series we summating PAK, if this is not infinity, then automatically or directly we can know the probability of limit supremum of AK must be equals to 0. Okay, so this is a Borel-Cantelli lemma. So if we impose this condition inside AK are independent, so that's why when AK is independent, are all independent, so we can have this equal two-way. Okay, we have two ways here. So that is okay. I think you can have this summating of PAK not infinity if and only if P of limit supremum of AK is equal to 0. Okay, so alternately you can say, or you can say this one is infinity if and only if this one is equals to 1. Okay, so this is known as our Borel-Cantelli lemma. So at the moment, just remember this. When this is not infinity, P lim sub AK will be 0. When this is infinity and AK independent, P lim sub AK is equal to 1. All right. Okay. Please chop down these two identity. Okay. So we just proceed to our question. So question 5. Question 5. Actually, there are two parts for question 5.
Is it really if and only if? Is it really two-way implication?
If and only it means two-way.
But then the textbook says only one. I mean, it says it doesn't say IFF.
Which one? You are talking about this, the one inside the bracket or the questions?
I'm talking about the Borel-Cantelli lemma, the second one.
Okay. Yeah. You look at here. This is the statement. Yeah, the statement. The former statement will be here. The first statement is when I'm just simply said the series. Okay. So when the series, okay, I just simply said this is a series. All right. When the series is not infinity. By the way, I just have a question. Can you guys see my cursor moving or nothing there? Inside the screen. Can you see my cursor moving? No cursor.
I see a mouse where it's not moving right now.
So like can you see the arrow moving on the screen? No. Okay. Then that's the thing, because you know when I move my mouse, they're supposed to have an arrow moving, can you see the arrow for my mouse?
Yeah, when you move your mouse, we can see.
I'm moving my mouse. Can you see the cursor moving, right?
Yeah. Can.
Yeah, okay, good. That is good. So that means you guys can see which part that I'm pointing now, right?
Yeah, can.
Yeah, okay, good. That's very good. Okay. I'm just okay. So you look at this one. I'm just simply saying this is a series. Okay. When a series is not infinity, so P lim sub AK 0. So this is the first statement. Without having the assumption that AK independence. Okay, so that means whether AK independence or not independence, we can always got these conclusions, right? So for the second one, when the series is infinity, we require additional assumption that is AK independent. Then this is 1. Okay. Right. So when we assume AK independence, so that means if we also assume AK independence over here, then these two must be identical. Okay. What we can see is like this. Okay, maybe I just do the first one. The second one, you can, the logic will be like over here. Before that, I think you can follow this symbol, so this arrow over here. And also, you look at 1 and 2, you look at the opposite of the arrow, so that will be like this. We also have this. This will be like this. So maybe when this is not infinity, implies this is 0. When this is not 0, which means this must be infinity. You get the picture. That is when P lim sub AK is not 0, then I'm going to have the value for a series must be infinity. Okay, that will be this one. Okay, so this one imply this, not this will imply not this. So likewise, we're going to have this. For the second one, if we assume AK is independent, okay, so then P lim sub AK not equals to 1 would imply the series will be not infinity. All right, so just like this. Okay, so here's the how we can verify these things. Okay, so let's look at this, how we can get it. We can check this using this way. Okay, first of all, let's say we always assume AK is independent. Okay, so we can have the first one here. So when this one is not infinity, okay, then I'm going to have P limit supremum of AK must be 0. So this is by the first Borel-Cantelli lemma. Okay, so we directly got this, right? And secondly, if we assume P of limit supremum of AK is equal to 0, I want to go back to this. When this one 0, this will imply that when this one is 0, which just meaning that P lim sub AK cannot be equals to 1, right? 0 means it cannot be 1. 0 means it cannot be 1. But according to here, when this is not 1, then this must be not infinity. So then I'm going to have, or actually this will imply that P of this is not infinity. So that's why we can have this also imply this. So if you're combining these two, then we can have summating P of AK not infinity if and only if P lim sub AK is equal to 0. Provided this is true, provided AK is independent. Okay, so this is why over here, yeah, although the original statement, this both original statements are one direction only, left to right, left to right. Okay. However, if we assume this, we impose this additional condition, AK always independence, into the first statement, then I have two directions over here. When this is independent, these two are equivalent. 0, it must be not infinity. Infinity, it must be 1. So that's why we also call this as a 0-1 law, because when AK independent, then P lim sub AK have no choice, must be either 0 or 1. Right. But anyway, this is actually out of the topics here. Just to let you know, we can have such a nice relationship, yeah, or phenomenon when we consider a sequence of independent events. Right. So let's go to our question 5. Okay, cannot see this. Okay, part A, maybe it's a part A. Part A is like, okay, we always suppose, we assume AK are independent. So then part A is when P lim sub AK is 1, then I'm going to have, this is always infinity. Oh, I think part B is easier. I think we don't. Hold on, I'll remove it. Assume AK is independent. So I think part B will be easiest. So when PBAK is infinity for every event B, okay, with PB not 0. So this will, we assume this. Okay, we assume this, and we assume, how should I say it? Maybe I should say this is a opposite direction. That will be better. We assume this is independence, and we assume this for only event. So what we can do is we can just simply take B to be omega. So because of this is true for any, right? This is true for any one of the event. We can just replace B with any event. Okay, so we just take B to be omega. Then we can have summating of P AK is equals to infinity. So I think this is clear. So this is just simply because omega intersect AK is always equals to AK. So then this is infinity. So now we have a hypothesis here. So number one, AK independence, and this is infinity. Okay, with these two hypotheses, then we can see hence I'm going to P lim sub AK must be equal to 1. Okay, so this is directly by using Borel, the second Borel-Cantelli lemma. Right, so this is straightforward for the first part. Okay, so the second part, so that is part A, actually this direction. Okay, one by one. First, I think statement number one. So we assume AK is independent. Okay? And statement two, we assume this P lim supremum of AK is equal to 1. Okay, what we want to prove? We want to prove this. You want to prove this. Okay, summating PBAK equals to infinity for any event B with PB greater than 0. This is what we want to prove. Okay, so what we can do is we can prove by contradiction. So what we can do is we assume the conclusion is not correct. Is false. Okay, so we assume the conclusion is false. So that means we assume this conclusion is not true. So what does it mean? So which means that we can find an event B with PB greater than 0 and this P of BAK is not infinity. Right? All right, so I think it's the logic is quite straightforward, right? So it's like okay, this is infinity for any event B. So this is the conclusion. So if we assume the conclusion is false, so that means we can always get an event whereby this is not infinity. Okay, so this is the simple logic that we can get over here. So we can find a particular event B. The probability is positive, and this is not infinity. Okay. Okay. When this is not infinity, then we have to go back to our Borel-Cantelli lemma. Okay. So I think maybe I should instead of using B, I use some other symbol. Might be better. Instead of A, maybe I change to some other symbol. It's a bit confusing over here. So just to let you know, this is actually true for any. So let's say I'm replace this with some other symbol. Let's say D. Okay. D. Okay. So if this is not infinity, so we're using this. When this is not infinity, so this must be equals to 0. Okay. So for this sequence of event dk, regardless they are independent or not independent. So that means we are taking dk to be b and ak over here. So then we can have this. So that is number 5. Then we can have p lim sup of b and ak must be 0. So what we can do is I'm taking dk to be b and ak. I have to look at the answer. How to do? Okay, so we have this, okay. Okay, next, again, this is our question 4. We have done this. Yeah. So I only look at it. So this is equal to this. Okay, so that's why this is 0, right? So that means I'm going to have this. So 0 will be equals to, so this will be P of Bn lim sub of AK. Okay, P of lim sub of AK. So when this is 0, then I can have this is equal to 0. Okay, next PB. Okay, PB can always be written as P of Bn lim sub of AK plus P of Bn, the complement of lim sub of AK. So this is you know, it just like this one is just refer back to question 1. Okay, what we have discussed just now. So we have a A1 and A2. So refer back to question 1. And this is 0. Then I'm going to have PB this is square and this is 0 plus this. This one. So which means this is greater than 0. Okay. And this one is less than, how should I say it? Okay, maybe I could simply say this. This part must be always less or equals to P of limit supremum of AK, complement. But according to our part here, you can see, okay, so according to this, we assume this is equals to 1. This is equals to 1, so this is equivalent to say that the probability of the complement of this must be equal to 0. Okay, so this is 0. Then we can have so this is equal to 0. Then we must have 0 less than 0. So because of this bit is equal to 0. Okay, so we can have 0 is greater than 0, and obviously, so this is impossible. So this is impossible. So hence, we can make a conclusion. The conclusion must be true. So that means this is our conclusion. This conclusion must be true. Right?
Sorry, how do we know that it equals 0 again?
You mean this part?
The last one, yeah.
Look at number 2. Number 2. Number 2 here. Here. My second line. Sorry.
Oh, okay.
Okay. So this is actually our questions, right? we assume this is independent. We assume this is our hypothesis. Okay, you go back to our questions. Yeah, we have two hypotheses here. First, it must be independent. Secondly, this is equal to 1, and I want to show this conclusion is correct. Okay, I will show this conclusion. So 1 and 2. Got it? So that's why we have two hypotheses here. The first hypothesis will be the sequence of AK are all independent, and the second hypothesis will be P lim sub AK is equals to 1. So this is equivalent to say that the complement for this event is having probability 0. Okay, so now we want to prove these conclusions. So I'm going to do it indirectly. That is, I just assume the conclusion is not true. Okay, assume the conclusion is not true, it's false. So when we assume the conclusion is false, which means we can find an event with positive probability, and this is not infinity. Okay. Okay, so this is the conclusion. This is infinity for any event B with positive probabilities.
Yeah, okay.
Okay, so I think the following, once we have the next one will be, yeah, I'm using, this is the Borel-Cantelli lemma. Okay, and the next one, this line to this line, I'm using the what we have got in question 4, right? This here. And next, this is this phenomenon that we have discussed in question 1. So just follow all these calculations, so we can get this feature 0 greater than feature 0 greater than 0. So, and this is cannot happen. So therefore, the conclusion must be true. That's the end for the proof. Question 11. Okay, question 11. Okay, what's wrong with my solution? I thought my solution is very obvious and very clear. Okay, so let's look at here. Yeah, 2 persons independently toss a fair coin n times. Okay, first keywords will be here. Okay. So that means I'm going to have 2 independent events here. So show that the probability that obtain equal numbers of heads is equals to a probability that together they get n heads. So again, 2 statements. So we have 2 events. Event number 1, they obtain equal number of heads. Okay, and event number 2, together they get n heads. Okay. All right, so then just follow the solutions. So what we can do is let x be the event. Not event, sorry. We define x to be the number of heads obtained by the first person. Okay, and y to be the number of heads obtained by the second person. Okay, so then I have 2 random variables, x and y, right? Okay, next, we assume this is a fair coin. Okay, so that means the probability of getting head and tail must be the same. So we define it, then we can see both X and Y must having the same distributions. The binomial distribution, N and P is half. Okay, X and Y are having the same distribution. They are binomial distribution with probability of getting head will be half. Okay, so the first event, they obtain equal number of head. So I think it's clear, right? So X is number of head obtained by the first. So this event will be X equals to Y. Agree? I think it's clear. The second event is together they get N head. So that means X plus Y is equals to N. Right. So now I just want to show this is the probability of this event. X equals to Y is equals to the probability X plus Y equals to N. These two are equal. Okay, so this is what, that's why we just look at the probability of X plus Y is equals to N. So I think this is straightforward. So this is equals to summating K equals 0 to N. P, X is K and Y is N minus K. So I don't think I need to explain, right? So this is clear. Okay. So X plus Y is N must be either X is 0, Y is N, X is 1, Y is 9, and so on. Okay, next will be here. We assume they are independent. Okay, when these two events are independent, so that means we can actually splitting these two. So then this is equals to summating K equals to 1, P of X equals to K, multiplying P of Y equals to N minus K. So this is clear because of X, Y independent. Okay, the next one will be the standard formula in distribution theory. So when your Y is a binomial distribution with n trial, the probability of success P, right? So then N minus Y must be also a binomial distributions, N tri and Q. Okay, so that means but in this case, and here in this case, P is half. So P and Q are both equals to half. So that means Y and N minus Y are the same distributions, are having the same distribution. So this will be equals to we summating P of X equals to K and P of N minus Y equals to K. So here P equals to half, Q equals to half. So implies that Y must be equals distribution with N minus Y. So this will end up to be this. And again, because of X, Y are independent, So then we can have this will be submitting K, P of X equals to K and Y equals to K. And this is just equals to the probability whereby X is equals to Y. Okay, so we have proved this. The probability of the event X equals to Y is equals to the probability of the event X plus Y is equals to N. Where is it? Where the first line? Yeah, this one. P of X plus Y equals to N is just equals to this. Wait, what question? Huh? Questions.
Question 6.
Question 8, sir.
6.
Question?
6.
I think someone asked for question 6, right?
Question 6. Oh, okay. Question 6 and question 8. Oh, okay. Question 6. Yeah. Oh, I skipped this one. Okay. So question 6. Oh, okay. XY independence, FG Borel functions prove that Fx and Gy are also independent. Okay, so again, just need to recall definitions. So it's definitions 3.2.1. So if we have two events, so we said that we have two random variable xy. So they are independent provided P of, we have put it down here, provided that the probability of X inverse A and Y inverse B is equals to P of X inverse A multiplying the probability of Y inverse B. For any event A, B. Okay, maybe instead of XY, since we have XY over here, I switch to another symbol so that you guys has a better picture what to substitute into the questions. So instead of talking about XY, I'm talking about UV, okay? UV. So let's say I have I should have a bracket here. Okay, a bracket here. Okay, supposing I got two random variables, U and V. So we said that these two random variable U, V are independent, provided that P of U inverse A and V inverse B is equal to P of U inverse A multiplying P of V inverse B for any events AB. Okay, so not to confuse. So this one is independence corresponding to random variable. Okay, this concept apply to random variable. So UV are independence random variable. So in other words, so you may use the language of event. You can say this. UV are independence random variable provided that U inverse A and U inverse B are independent events for any event AB. Okay, so those we are using independence in both lines. Okay. However, in the first line, the independence are corresponding to random variables, whereas in the last line here, the independence are corresponding to events. So this is the definition for independent random variables here. Okay, go back to our questions. I think it's quite difficult here. So XY independence, FG Borel, we want to prove that FXGY are also independence. Okay, so that means I want to substitute U to be F composite X and V to be G composite Y. Okay, want to replace UV by FX and GY here. Yeah, so that's the way how we apply this definition to solve this problem here. So I hope you get ideas. Okay, what I want to do is I want to show this P of F composite X inverse A, G composite Y inverse B equals to P of for all event AB. Okay, so this is what I want to do. I just want to show this one equals to this. All right, so now let's do it. Let's consider two events A and B. So let's begin with this line, P of F composite X inverse A and G composite Y inverse B. Okay, so this is we know this, so this is equals to the inverse of X inverse of F over here. So this is actually again calculus, something from calculus. Okay, so this is from calculus. You may refer to what you have learned in calculus. Okay, so if you have two functions, F composite G, F composite G inverse will be G inverse composite F inverse. Okay, so that's the way for it. So now we applying the properties of X, Y are independent. So that means now we can have this will be P of X inverse, F inverse. Okay, multiplying this P of Y inverse. This. So this is true because of we know X, Y independent. Okay, and F inverse A, G inverse B are events. Okay, now we applying back these properties or this identity into here, then we can get back this line. This will be equal to P of F composite X inverse of A multiplying P of G composite Y B. So again, we have achieved what we want to do over here. So like I said, the purpose will be we want to show this left-hand side equals to this right-hand side here. Then we have got it. So we just have shown this equals to this. So once we have able to verify this, then we can make a conclusion. Hence, f of x and g of y are independent. Number 8.
Oh, actually, for number 8, I just want to clarify, because we show that it is dependent. So then like how in number 6, when we show that x and y are independent, so any function of x and y are also independent. Can we say the opposite? Because that's what we do here.
What is the answer? Let me see what is the answer first.
Yeah.
What is the answer first? Answer is no. Answer is no. Okay. Answer is no. Okay, here's the answer. So the answer is no. Right? How to? Okay. So when we have an indicator functions, so we have, if we consider indicator function or indicator random variables, so we have a relatively easy way to verify it. Okay. Did I put it in my lecture notes? Okay. Just a remark for you guys. When we consider general random variable xy, so that is more complicated. So then this is the way that we can do in general. Okay. Alternatively, we can use the PDF. Okay, the density function for xy, or we can look at the distribution function for xy to verify it. Okay, when we come to this indicator function, we have a relatively easy way to verify it. So let's say we have this 1a and 1b are independent. Okay, of course, here independent as random variables. Okay, provided that A and B are independent as events. So that's why what you can do is actually you want to check whether these two indicator functions, 1a and 1b, are independent or not. You just need to check whether A and B are independent or not. Sorry, I didn't prepare for these questions. That's why I can't remember whether I have put this in the lecture notes or not. But anyway, you can remember this, okay? Right? A, B are independent as events. Okay, A, B are independent as events is equivalent to say that the indicator function 1a and 1b are independent as random variable. So that's why in this question is quite straightforward. Okay, quite easy. You want to check whether this x and y are independent or not, because x, y are indicator function. So you just need to verify these two events are independent or not. So that's the way.
Yep, got it.
Thank you. Right. So that's why the answer will be like this. We just verify this. Okay, the answer will be this one. So we just check PA and PB. So we can see PA and B is not equal to A times PB. So therefore, XY are not independent. Okay. Okay. I think, wow. Okay, just nice. We have spent 1.5 hours for our tutorial sections. So just nice. I think it's a time for us to take a break as usual. So we continue our lecture, the discussion on chapter 5 after 8 o'clock. All right. Okay. So as usual, we have a break until 8 o'clock. Huh? Okay. See you afterwards.